Hi, my name is Denis O'Carroll. I'm a professor in civil and environmental engineering at the University of New South Wales. I serve as the Independent Monitoring Committee representative for the Orica Botany Bay remediation site. Today I'm going to talk to you about some outcomes of the strategy workshop that was held by Orica, where they invited in international experts in March 2020 to discuss the status of the remediation at the site. So today I'll talk to you a little bit about the current status of the remediation products, the groundwater treatment plant, and pumping, limiting the further movement of the contaminant to the estuary, and some thoughts maybe on what the future will look like. So what types of contaminants are on site? We have predominantly tetrachloroethylene, or PCE, and that was used in dry cleaning, degreasing, and a range of other industrial activities. We also have carbon tetrachloride on site, and that was used for cleaning, degreasing, fire extinguishing, and also in pesticides. We also have what's called trichloroethene, or TCE, and again used in degreasing of metal parts, in refrigerants. And we also importantly have 1,2-dichloroethene, ethane, and 1,2-DCA or EDC. And again, that was used in a wide range of products, including making PVC pipes. Importantly on site, we also have other chlorinated contaminants, and those could be a range including hexachlorobutadiene and hexachlorobenzene. They're present at low levels, but they are of concern, and we're going to talk more about them today. Here we have a map of the site, and in black you can see it's delineated. That's the Botany Industrial Park, and the red spots throughout that, or inside that, those represent the source areas, or the zones of very, very high contamination. We're going to talk a lot more about them today as well. Just to orient, this is Springvale Drain that goes sort of through the site, and it discharges down into Penryn Estuary near the port. Groundwater flows through the Orica Botany Bay site and towards the Penryn Estuary. So contaminants that would be underlaying the Orica site would migrate potentially to Penryn Estuary if Orica didn't do anything to stop the contamination from reaching the Penryn Estuary. Again, here's a zoom in of the site, and you can see here the different source zones. On site, it's estimated that there's between 9,600 tons and 19,400 tons of contamination below the ground, which is quite a lot. And then you can see it's in different hotspots here that I've identified in red circles here throughout the site. And N1 and N2 sort of at the top of the site there, there is contamination there, but it's of lesser of concern than the other ones that I've highlighted in red, which as you can see, there's upwards of thousands of tons of contamination below the ground that are of concern and that would cause contamination. So to give you an idea of the magnitude of the site and the contamination, I've highlighted in blue here the Orica Botany Bay site, so near Botany Bay, and compared it to Sydney Olympic Park. And it's about the same size as Sydney Olympic Park. And to give you a sense of the amount of contamination below the ground, we can look here. I've highlighted in red in the Sydney Olympic Park the Olympic pool. And the amount of contamination below ground at the Orica Botany Bay site would fill 6 or 7 Olympic-sized swimming pools with the contaminants. So quite a bit of contamination at the Botany Bay site. In the graph on the bottom right, you can see that Orica, since they've started operations of the plant, have removed thousands of tons, or just over 1,000 tons of contaminants from the ground. And you can see that depending on how you look at it, you can see that the lines show that they continue to extract contaminants with time, but it's the law of diminishing returns. They're not on an annual basis removing as much contaminants as they were historically. That being said, though, the plant is still quite protective of the environment and continues to remove these important contaminants from the subsurface. Here again is the site, and what Orica has placed 3 rows or lines of extraction wells. And for those extraction wells, what they want to do is pump down the groundwater here so that the contaminants flow in towards a well. And you can see Penryn Estuary on one side. What you want to do is pull water away from Penryn Estuary and in towards the well, so stop any contaminants from getting into the estuary. And just sort of like a sink when you have a drain. All the water flows in towards that. So then what you can do is stop the contaminants from going where you don't want them to go. Now also in the site, there's contamination in an area called Southlands. And that is, historically, they identified the possibility of an unlined drain that may have led to contamination in that area. The contamination levels are quite high, and Orica and the consultants have tried to go and find this potential drain and has not been found. So unsure if that ever did exist. But having said that, there are still contamination in that area. How it got there is uncertain, but it is of concern and needs to be dealt with. Now, looking at zones of high contamination, this is based on a report that was presented to us at the workshop, and sort of getting a sense of how much contamination is there. This was done by Golder Associates. They sampled 200 sampling locations in 52 distinct wells. And then sort of try to sort of get a sense of, how do we define what is really contaminated and what does that mean? I've gone and looked at this US EPA report and guidance document, and you can see here, this is what happens when contaminants get into the ground. The red is the contaminants, much like you would have at Orica Botany Bay. They're denser than water, so when they seep into the ground, they'll smear out, they'll dissolve a little bit, not very much, because they're not very soluble, and they'll keep going down until they hit clay barriers or bedrock where they'll reside. We'll talk a little bit more about that. And you can see that here in this schematic. And importantly, at Orica, there's a lot of peat in the subsurface. And what the big concern is that as the contaminants migrates down and maybe laterally as well, it'll be sucked up in these peaty layers and it limit its movement down gradient. So it'll act as a long-term, persistent source of contaminants. And here I've just going to show you a little bit of a sandbox experiment. You can see the sandbox experiment that I did with a PCE, which is a chlorinated solvent that is at the Orica site. This sandbox is, it's about 30 centimeters by 30 centimeters, and it's packed with sand, and then there's some little fine lenses of sand in there. So here you can see that the contaminant, as it's released, it migrates down to the fine lenses, and then it'll be wicked up on the lens at the left, and that's much like the peat in the subsurface at Orica, where the contaminant will stick in there and persist potentially for very long amounts of time. So this liquid here, which is dyed red, would have been released to the subsurface at Orica, and you can see when it is released, it disperses quite readily across the sand tank, and there are some zones of very, very high saturation. And we would sort of conceptualize the subsurface at Botany Bay to be something like this. So which makes it, the first thing is finding the contaminant is sometimes hard because you don't know exactly what it's like in the subsurface. And then two, there's these zones where you have very, very high saturations, and they would persist in the ground, act as a long-term source of contaminants, which is a significant concern. So at the Orica site, do we have this type of high saturation chlorinated solvents, this high contamination areas? So looking at these zones, and what I did in the analysis is I calculated what's called the effective solubility. Now, if a contamination on site, if the concentrations are what's 1% of the effective solubility. That's considered a quite high and heavily contaminated area. So I looked specifically for those types of concentrations. That was 1% of the effective solubility. So when we did this, what I did is, to be a little conservative, is I looked at the instead of a 1% threshold, I said, okay, let's change it to a 10% threshold. So that would represent very, very high concentrations in the subsurface at this site. And you can see here at a range of locations around the site, there are zones of very, very high concentrations. And that's these well locations circled in red, and then the different depths. And largely at the site, you can see most of the zones of high concentrations, they're quite deep. You know, let's say on the order of here, let's say 12, 16, 18 meters. They are right here. You can see that they're in the area of that suspected unlined drain. So there's reasonable amount of high concentrations there, which is obviously of concern. And then off-site, getting closer down to Foreshore Road here, or Penryn Estuary, there's also a bit of off-site contamination. So there's contamination sort of throughout. And if you look at the sampling locations, there's 35 of the 200 sampling locations have greater than the 10% threshold, and 64 of the 200 locations have greater than the 1% threshold. So that US EPA threshold for extremely, that would denote extremely contaminated. So if you just look at the wells, 14 of the 52 wells have higher than the 10% threshold, or nearly half of the sampling locations of the wells have higher than the 1%. So a good amount of the sampling locations on site are quite contaminated, which is a concern. So questions are: does the strategy change in future? Well, and that is a big concern. Can we turn off the plant? We don't want to have a long-term source of contamination. Concerns are Springvale drain. If you did turn off the plant, or you change it, you always want to be protective of these drains and any fast conduit of contaminants getting into the Penryn Estuary. And Springvale drain was highly contaminated in the past. It is not believed to be now. And you can see here that there's a significant contamination plume. That's what's here, dyed in red, or colored in red, migrating from the plant to the estuary. And the structure of the subsurface would look something like this. In terms of the contamination, is very spread out and dispersed. So trying to get access to that and to clean it up and figure out where it is a little bit of a challenge. One thought for remediating the site is to use the naturally occurring bugs. And geosyntech consultants looked to see whether natural attenuation mechanisms would serve to accelerate the remediation, to clean up of the site. So what they wanted to know is, are the bugs on site, are they going to be able to degrade the contaminants? And that does happen, but will it happen at this site? So you can see here, and this is a little bit complicated, but you can see the contaminants goes from a parent compound, and then let's say it takes the half-life is 2.5 years from one contaminant to the next, and then it could be from another one for just 1 year. And on the right-hand side here, you can see it's just 22 days. But let's say for some of the most important contaminants on site, the half-life might be on the order of 2.5 years. So you can see that there. So if we take, let's say, a zone of high contamination here, and this is for trichloroethene, or TCE, and it's present at this location at 15 milligrams per liter, which is pretty high. And let's say your end goal was to want to have drinking water quality, and that's very unlikely that you would ever expect to be able to drink from this aquifer in future, but let's say that's something that was a goal. So let's say that you started here on the graph at 15 milligrams per liter at time 0, and then the half-life is 2.5 years. So after 2.5 years, you would reduce the concentration to 7.5 milligrams per liter. So you've halved it, and you're getting half there. In another 2.5 years, you get to 3.75 milligrams per liter. So you can see you're decreasing the concentration. So still though, after 5 years, they're obviously well above the WHO drinking water guideline. As you keep going down, it would take on the order of 20 years, if the half-life is 2.5 years, to completely degrade the contaminants on site and get to that WHO guideline. So this is what it looks like, and will the strategy have to change in future? Will we? The questions are: can we adopt these natural attenuation mechanisms to get the bugs to clean up the site? And this is essentially what you want. Let's say you have TCE, you've got some kind of a microorganism, and you want to degrade the TCE to, let's say, something like ethene. And you can do that, let's say, if it's dissolved, it might be easy. It's a little bit harder when it's in a free phase, when it's a liquid, when you have a liquid contaminant. They're not dissolved in water. So the questions are, do you get from TCE to ethene, and how fast on this site? Do we have the right type of bugs to do it? And looking at this US government report, they again say that you need on the order of 10 to the 6 gene copies, which is sort of the number of bugs per liter, which is quite high. They need that to remediate the site. So let's use that sort of as a threshold. And you can see Geosyntec did a great job, and they characterized the types of bugs that are present on site and the quantity. And you can see here that it's a little bit hard to see, but you can see the numbers on the y-axis and all the different wells that they sampled. And importantly, you can only see sort of on the right-hand side, let's say in cluster 4, maybe in cluster 5, you can see there's only a couple of locations where there's lots of bugs. So there's only a couple of locations on the entire site where there's possibly enough bugs to clean up, to degrade the contaminant. I personally would have concerns regarding natural attenuation, whether or not at the moment, if the bugs could clean up the significant contamination on site. And that's in part because there's DNAPL, this dense free non-aqueous phase liquid present on site. So it's as a liquid, not dissolved in water. And that's really challenging to clean up. And also the relatively low microbial community population. So the bugs that would actually clean it up, they're relatively low in concentration on site. So there are ways to get around that. You might what's called bio-augment or biostimulate, get the bugs to grow up such that they can proliferate and clean up the contamination. That would be ideal, and everyone would be quite pleased with that outcome. So some wrap-up discussion items. There are very high contaminant concentrations throughout the aquifer, and I think I showed you that when I was all those circles when I was showing zones of high concentrations based on a US EPA guidance document. So there is still a considerable amount of contamination on site, and then because of that, the groundwater treatment plant and the pumping will likely have to operate for the indefinite future for quite a while, because it's not going away quickly, and you have to have the pumping wells operating so that the contamination doesn't get to the aquifer. And at the moment it's not, and Orca is doing a good job of mitigating against it getting in there. And unfortunately, at the moment, natural attenuation mechanisms are unlikely to be able to clean up the aquifer without help. So potentially you could engineer the system and help the bugs. You could put in some food so they grow up, or put more bugs in, the ones that will clean it up, so that they will act faster. But that's a little bit of a challenge, but certainly it could be looked at as an alternative to help accelerate the cleanup of the site.